In this lecture, we will look at how neurons communicate. Neurons transmit two types of signals using action potentials and neurotransmitters. Action potentials are high-speed transmission of electrical signals along the axon of a neuron. The electrical signals are generated by the diffusion of ions across the axon membrane. The ions involved will be sodium and potassium ions. When an action potential arrives at the axon terminal, it triggers the release of a chemical known as a neurotransmitter. The neurotransmitter then diffuses across the synaptic gap and binds to another cell, which can be a neuron, muscle, or a gland. Let's recall diffusion. Diffusion is the movement of molecules from a region of higher concentration to a region of lower concentration. Because of the mainly hydrophobic nature of the cell membrane, ions need to use transporters such as ion channels and carrier proteins to move in and out of the cell. Before we discuss how an action potential is generated in an axon, let's see an axon at rest. At rest, when there is no stimulus present, there is an unequal distribution of ions on both sides of the axon membrane. There are more sodium ions outside and more potassium ions inside. How does this unequal distribution of sodium and potassium ions arise? There are a few reasons. One reason is due to the presence or the action of the sodium-potassium exchange pump, which pumps out 3 sodium ions and pumps in 2 potassium ions against their concentration gradients using ATP. A second reason is due to the presence of leaky potassium channels. These leaky potassium channels are always open. So potassium ions, which accumulate in the axon thanks to the exchange pump, can leak out of the axon down their concentration gradient. The end result is that sodium ions become more concentrated in the extracellular fluid, whereas potassium ions become more concentrated inside the axon. Thus, there is a net positive charge outside the axon and a net negative charge inside the axon. This separation of charges can be measured by inserting one electrode into the axon and placing another electrode in the extracellular fluid and it measures about minus 70 millivolts in a resting unstimulated axon. So if we were to measure the membrane potential, this would be how it looked like. On the x-axis, it will be the time. On the y-axis will be membrane potential measured in units of millivolts. So at rest, the membrane potential is about minus 70 millivolts. There are more potassium ions inside and more sodium ions outside, and there is an uneven exchange of sodium and potassium ions, resulting in the membrane potential being negatively charged on the inside relative to the outside. Now, suppose that a strong stimulus arises. Okay, we apply a stimulus at this point. This causes the sodium channels to open suddenly and sodium ions to rush into the axon down their concentration gradient. Now, there are more positive ions inside the axon, and this causes the membrane potential to spike and become more positive, changing from a negative 70 millivolts to a value of about positive 30 millivolts. This is the first phase of the action potential known as depolarization. Meanwhile, the potassium channels remain closed. It is important to note that the stimulus must be strong enough to hit a threshold of about minus 55 millivolts before a full-blown depolarization actually happens. Okay, so the stimulus need to be strong enough to hit a threshold of minus 55 volt. If the stimulus is weak, then what we will see is that a few sodium channels will open, but they will close again. Therefore, there is no depolarization. The second phase of the action potential is known as repolarization. Repolarization is to restore the membrane potential from a positive value to a negative value. Okay. In order for repolarization to occur, now the sodium channels close and it is the turn of the potassium channels to open. As a result, potassium ions rushed out of the axon down their concentration gradient. Now, there are too many positive ions being lost from the axon, and the membrane potential drops towards the resting value of minus 70 millivolts. So we will continue plotting this on the graph. This depolarization marked by the opening of the sodium channels, and the next phase will be the opening of the potassium channels, which will try to restore the resting membrane potential. Okay, this is known as repolarization. Potassium channels not only open slowly, they also take their time to close. So for a short period, there are too many potassium ions lost from the axon, and the membrane potential drops below minus 70 towards a value of, let's say, minus 80. Okay, so this part here is due to the slow closing of the potassium channels. Eventually, all the potassium channels will close, and thanks to the sodium-potassium pump and the leaky channels, the membrane potential will be restored to the resting value. So to summarize the action potential, depolarization is due to the opening of the sodium channels, and when sodium channels open, they rush into the axon. This will cause a reversal of the membrane potential from a negative value to a positive value of about 30 millivolts. The next phase of the action potential is repolarization, which is to restore the resting membrane potential. In order to do this, the sodium channels will close and the potassium channels open. When the potassium channels open, they will rush out of the axon. Eventually, the potassium channels will close. So something around here, they will start to close. And because they take some time to close, for a brief period of time, the membrane potential will actually drop below minus 70 towards a value of minus 80. We say the membrane now is hyperpolarized, more negative than at rest. With time, progressively, potassium channels will close, and with the help of the sodium potassium pump and the leaky potassium channels, the membrane potential will be restored to a negative value of minus 70. It is important to note that the stimulus need to be strong enough to hit a threshold of minus 55 volts before we can actually see depolarization happening. Some characteristics of the action potential. The action potential is all or none response. So initially a few sodium channels will open. When the threshold is reached, many more sodium channels will open. And when they open, there's nothing to stop them from opening. The stimulus need to be strong enough. When the stimulus is weak, there will be no action potential. The height of the action potential is always the same. That means once depolarization happens, it will always hit positive 30 millivolts. If a stimulus arises while an action potential is still happening, then there will be no second action potential. We have to wait for the action potential to complete the repolarization and hyperpolarization phase before another action potential can occur. Sodium channels open fast and close fast as well. Potassium channels open slowly and close slowly. So the channels that are involved in the first phase of action potential will always be sodium channels. The channels that are involved in the second phase of repolarization of the action potential repolarization will see the potassium channels in action. The sodium and potassium channels involved in the action potential are what we refer to as voltage-gated or voltage-sensitive ion channels. These channels open when they sense ions. For example, if we apply a stimulus by injecting some sodium ions into the axon, the voltage-gated sodium channels will open. Okay, so these are sensitive to presence of ions. We have seen that the axon can be quite long. So how does action potential move along the axon towards the axon terminal? So during depolarization, when the sodium ions diffuse into a segment of an axon, they will spread to the next adjacent resting segment of the axon. Okay, so suppose this is part of an axon and there are 3 sodium channels there. Action potential is traveling in this direction, starting from the axon hillock towards the axon terminal. This sodium channel here was previously has just completed the depolarization, so now they are in what we call a refractory state. Okay, refractory. Refractory state means that they are currently now inactive. Okay, it will take a while for them to open again. So the sodium ions that are inside now will diffuse and stimulate the adjacent sodium ions to open, and this will cause more sodium ions to rush into the axon. And similarly, the sodium ions will diffuse to the next segment of the axon and stimulate these other sodium ion channels to open, and so on and so forth. So the action potential is traveling along this direction. Any sodium ions that were previously open will be in a temporary refractory state. That is, they are not sensitive to ions. When the axon does not have myelin sheath, action potential can be recorded at every point along the axon. However, when an action potential is present, ion movement can only be detected at the nodes of Ranvier, where there are no myelin sheath. So at the nodes of Ranvier, there are many sodium and potassium ion channels. Thus, the action potential will appear to jump from one node to another. Okay, jumping. This type of transmission of action potential is what is known as saltatory transmission, the jumping, the leaping of the action potential from node to node. The speed of transmission along a axon that has myelin sheath is a lot more faster than the speed of transmission along an axon without myelin sheath. Next, we will see how the action potential gets converted to a chemical signal and gets transmitted to another cell.